In this video, we discuss learning outcome number 2 of lesson 9.2, which is about testing a claim about two means with sample data collected from two independent samples. And specifically, we're going to focus on the p-value method. Here, we're going to assume that the population standard deviations are unknown, and we're not going to assume that those population standard deviations are equal to each other. I'll also list equivalent methods for testing a claim about two sample means when the population standard deviations are not known and assumed not to be equal to each other, or not assumed to be equal to each other. And then we'll describe the rationale behind the formulas and procedures used, not just for the p-value method, but for the critical value method and the confidence interval method as well. We are going to focus on the p-value method in this video. So after we discuss the rationale behind the formulas and procedures for all three methods, we'll do an example of the p-value method, but the rationale for all three methods is in this video, rather than the videos about the confidence interval method and the critical value method. Now, in order to talk about the difference between two means, two population means, we need to talk about the distribution of the difference between two sample means, and that requires going back to what we know about the sampling distribution of sample means x bar. We initially talked about this for the first time in this course in lesson 6.3 when we talked about sampling distributions. So remember how this works. You've got some larger sample, and you randomly select n values from that sample, and you compute a sample mean x bar. And then you do that again, and you do that again, and you do that for all possible samples of the same size n. And then you look at the sample means, and then you say, what is the distribution of those sample means? What's the distribution of x bar? Well, it turns out under certain conditions, those sample means will tend to have a normal distribution, and it's going to look something like this. So again, all possible samples of the same size n are selected. For each of those samples of size n, we're computing an x bar, that's our sample mean, and then the distribution of the sample means is this. It turns out that the mean of the sample means is actually equal to the true population mean that we're trying to estimate. That's a very good thing, because this sample mean, x bar, is intended to estimate the population mean. What this first statement says is one property of the sampling distribution of x bar is that the mean of the sample means, or the expected value of that sample mean, is the exact population mean that we're looking for. So we say that x bar targets that population mean, and that's a very good thing. That's the definition of an unbiased estimator. Now, it turns out that the sampling distribution of the sample means has a standard deviation, sigma sub x bar, and it's given by the original population standard deviation divided by the square root of the sample size. And if you want probabilities that x bar will lie in some range, those are going to be represented by areas under the curve, where this curve is given by, or this curve is a probability density function that describes this sampling distribution of x bar. Now, here is some notation for inferences about means with independent samples. We're going to use mu sub 1 to represent the population mean for the first population. X sub 1 bar as the sample mean for the first population. Sigma sub 1 is the population standard deviation for the first population. S sub 1 is the sample standard deviation for the first population. And N sub 1 is the sample size for the first population. So we're just using all the same variables that we're accustomed to using. We're just adding this subscript 1 to say if it has a little 1 as a subscript, that is referring to the population mean, sample standard deviation, population standard deviation, and sample size for the first group. If you change all those subscripts to 2s instead of 1s, those are the population mean, population standard deviation, and sample size for the second group. And that group is associated with a population. Now, all of that was just background so that we could talk about this distribution of a difference between sample means, x sub 1 bar minus x sub 2 bar. Now, since x sub 1 bar and x sub 2 bar are sample means for two independent random samples, the distributions of each of those are going to be approximately normal. And if the distributions of each of those variables is approximately normal, the distribution of their difference is also approximately normal. And it turns out that the mean of that difference is equal to the population difference, or the mean is equal to the difference between the true population means mu sub 1 and mu sub 2. And then we have a couple of ways that we can measure variation. We tend to focus on standard deviation and variance as measures of variation. Now, this is just a reminder of some notation and some terminology. Remember that sigma sub x bar represents the standard deviation of the sample means, and typically it's represented by this formula on the right-hand side, but we could also write it this way. We could write it as the square root of that population standard deviation squared divided by the sample size n. Sometimes, rather than calling this the standard deviation of the sample means, it's called the standard error of the mean, or sometimes you'll see it abbreviated SEM, or sometimes people won't say standard error of the mean, they'll just say standard error. Keep that in mind. Now, it is a fact that the variance between differences of two independent random variables, and that's what we have. X sub 1 bar is an independent random variable from X sub 2 bar because we have two independent samples. It turns out that the variance between that difference of those independent random variables is actually equal to the sum of their variances. It's not the difference of their variances like a lot of people think, it's the sum of their variances. So the variance of X sub 1 bar minus X sub 2 bar is equal to the variance of our first variable plus the variance of our second variable. And if we apply this formula up here, down here, by just squaring both sides, we get this. The variance of our first variable is sigma sub 1 squared over n sub 1. So it's that first population standard deviation squared over the sample size. And the second variance looks just like it. We just use 2's for subscripts instead of 1's. And then we add them together to get the variance of this difference. That's the variance of the distribution of X sub 1 bar minus X sub 2 bar. Now, most of the time we don't work with variance, we work with standard deviation. So we'll just take the square root of both sides. And now we've got the standard deviation of X sub 1 bar minus X sub 2 bar is the square root of this expression here, which is the variance. And I've got a picture up here. It's just sort of showing you again that this is our distribution of X sub 1 bar minus X sub 2 bar, and the mean of the difference between the two sample means is actually the difference between the two population means. And I put this little dotted line here so that you could remember the mean is in the middle, just as you would expect. Now we're going to talk about equivalent methods for testing claims about means on this slide. It turns out that when you're talking about two means, the p-value method, the critical value method, and the confidence interval method are all equivalent to each other. Now, one justification for that is that the p-value method and the critical value method use the same estimate of the standard error of the mean, or the standard deviation of the sample means, to compute our test statistic t. Since they use the same test statistic t, and the p-value method gives you an area beyond the test statistic, and the critical value method compares the test statistic to a critical value of t, and it sees it is based on determining whether that test statistic t lies in the critical region or not. The p-value method and the critical value method are always going to come up with the same result. We're using the same formula for our test statistic. Just in the p-value method, we're comparing areas. With the critical value method, we're comparing values on that horizontal axis, but we're going to end up with the same results. Now, when I say the same results, what I'm saying is all three of these methods, the p-value method, the critical value method, and the confidence interval method, all of them are going to say the same thing at the same time. So if we're working with the same data sets and the p-value method tells you that you should reject the null hypothesis. If you had used the critical value method or the confidence interval method, those two methods would have told you to reject the null hypothesis as well. And if one of the three had told you to fail to reject the null hypothesis, the other two will have told you to fail to reject the null hypothesis as well. So in other words, all three methods are going to tell you to make the same decision about the null hypothesis. And this statement here just says that one of the reasons that that's true is that both the critical value method and the p-value method are using the same standard deviation in their formula to compute that test statistic, and therefore we get the same results. Now, when you're talking about the confidence interval method, it is a little bit different, but we're using the same estimate of that standard deviation of the sample means, also known as the standard error of the mean, when we compute the margin of error, as we used for that estimate of the standard error, or when we're computing our test statistic for the p-value method and critical value method. So that's one reason that you would expect the confidence interval method and the p-value and critical value methods to get the same result. Now, another reason is that the t-value used in the formula for the margin of error E will actually be the same as the absolute value of that critical value of t used in the critical value method. So that margin of error is that t-value times an estimated standard deviation. We're using the same t-value here and the same standard deviation here when we compute our margin of error as we would use in the critical value method. So the critical value method and confidence interval method are equivalent to each other, and the p-value method and the critical value method are equivalent to each other. So all three are equivalent to each other. Now, if you're saying to yourself, I thought that wasn't how it worked, I want you to note that this is applying to differences between means, not proportions. This is true that all three methods are equivalent to each other when we're talking about differences between mu sub 1 and mu sub 2. But when we start talking about differences between p sub 1 and p sub 2 proportions, it turns out that the p-value and critical value method are equivalent, but not the confidence interval method. So remember, with the means, all three methods are equivalent to each other. With proportions, they're not equivalent to each other. And the reason is with proportions, the estimated standard deviation that we use is different when we are assuming the null hypothesis is true, as opposed to when we have no reason to assume that the null hypothesis is true in the confidence interval method. But for right now, know that all three methods are equivalent when you're talking about differences between means. Okay, so now let's outline the procedure for testing a claim about two means in the case where we've got independent samples. And I'm saying here on this slide with the p-value method, but the steps are the same for the critical value method as well, at least at the very beginning. This first two slides apply to both the p-value method and the critical value method. The first thing we want to do anytime we're doing some kind of statistical analysis is we want to check to make sure that the requirements are satisfied. Now, in order to use the method that I'm about to outline for you, we need to assume that sigma sub 1 and sigma sub 2, those are our two population standard deviations, those are unknown, and we are not assuming that they're equal to each other. If they are known, we'll handle that differently. If they are equal to each other, or we have reason to believe that they're equal to each other, we would handle that differently as well. But for the methods of this section, or at least for the beginning of this section, we're assuming that those two standard deviations are unknown, and we have no reason to assume that they're equal to each other. Our samples need to be independent, and they need to be simple random samples for these methods to apply. And then the last condition is this. Either both sample sizes are large, so both sample sizes are greater than 30, or both samples come from populations having normal distributions. If these requirements are satisfied, then we can say that the sampling distribution of the sample means is approximately normally distributed. And that means it's appropriate to use the p-value method, the critical value method, or the confidence interval method that we're going to talk about in the next few videos. Now, after you've checked to be sure that those requirements are satisfied, you want to write the claim in symbolic form and then use it to infer the null and alternative hypotheses. Then you want to either identify the sample sizes, sample means, and sample standard deviations, or compute them if the sample's original sample data was given to you. Usually we'll use technology for that, but you could also use the formulas that we discussed back in chapter 3. If you have a very small sample size, you can do it all by hand if you want to. And then just to emphasize meaning, why you're doing what you're doing, I encourage my students to graph a sampling distribution of x sub 1 bar minus x sub 2 bar, assuming that the null hypothesis is true, and then label that sample statistic x sub 1 bar minus x sub 2 bar from our two samples on the graph. Then you can visually see where x sub 1 bar minus x sub 2 bar lies compared to that mean. We're assuming that mean of the distribution is mu sub 1 minus mu sub 2, which will be assumed to be 0, given that the null hypothesis is true. And then you can ask yourself, you can look at that graph and then ask yourself, is this x sub 1 bar minus x sub 2 bar that we have significantly high or significantly low? Creating that graph doesn't help you answer that question, but it often helps you frame that question and really understand what it is you're doing and why you're doing it. Now, in order to determine if that x sub 1 bar minus x sub 2 bar is significantly high or significantly low, the next thing we do is compute the test statistic t corresponding to that difference. Now we're going to look at the distribution of the difference between sample means again on this slide. But now we are thinking of it in terms of, or in the context of, a hypothesis test. Now remember, when we're conducting a hypothesis test using the p-value method or the critical value method, we are going to assume that the null hypothesis is true, which is the same as assuming that mu sub 1 minus mu sub 2 is equal to 0. In that case, the mean of the difference between the two sample means is equal to the difference between the two population means. Since we're assuming the null hypothesis is true, we're assuming that that mean is 0. So we're assuming that the mean of this distribution is equal to 0. So I've got a 0 right here in the middle. And then we would have measures of variation that are necessary in order for us to convert between this x sub 1 bar minus x sub 2 bar that we have into the test statistic t that we'll want and need here. Now, in order to do that, we have to remember that fact that we talked about earlier. The variance of a difference between two independent random variables is actually the sum of their variances. This is the variance of x sub 1 bar. This is the variance of x sub 2 bar. You add them together and that gives you the variance of the difference between x sub 1 bar and x sub 2 bar. Now, most of the time we don't work with variance, we work with standard deviation. So we'll take the square root of both sides. Now, we're assuming in this case that we don't know that population standard deviation for either one of our populations. So they're both unknown. We have no reason to assume that they're equal to each other. So we're not going to assume that they're equal to each other. In that case, we're going to replace those two population variances with the sample variances, s sub 1 squared and s sub 2 squared. And then rather than using the standard normal distribution, we're going to use the student t distribution. And then again, we're going to take the square root of both sides. So we're replacing sigma sub 1 and sigma sub 2 with s sub 1 and s sub 2. And we're saying that the estimated standard deviation of this difference between sample means is equal to this. Then I just wanted to revisit that question. The question is, if the null hypothesis is true, is the value of our test, or is the value of our sample statistic, x sub 1 bar minus x sub 2 bar, significantly high or significantly low? Now, in order to answer that question, we convert to a student t distribution. So we're going to use the mean of the sample means and an estimate of the standard deviation of sample means in order to convert from this distribution of x sub 1 bar minus x sub 2 bar to a distribution that is given by the student t distribution, or is a particular student t distribution for a particular sample size. Now, this is a lot like converting from an x value to a z-score. We're just computing from this difference, our random variable in this case is x sub 1 bar minus x sub 2 bar. And instead of converting from that to a z-score, we're converting from that to a t-score. So we take that difference and we subtract the mean of the distribution it came from, and we divide by not the standard deviation of the distribution it came from, but this estimate of the standard deviation. I've just got an S here instead of a sigma to represent that estimate of the standard deviation. That's going to give us a t-score. Now, the mean of the difference between those two sample means is actually equal to this, and I see some parentheses that are missing right now. I'm going to fix that. There we go, I fixed it. So this mean of the difference between the two sample means is mu sub 1 minus mu sub 2, and this estimated standard deviation of this distribution on the left is equal to the approximate standard deviation, which is given by the true standard deviation with the population standard deviation sigma sub 1 and sigma sub 2 replaced by S sub 1 and S sub 2. So this is the formula that we use to get the test statistic t. Now, most of the time I use something like Excel to work this out. Looks like there's a lot going on, but it's just substitution. You just plug it in and then simplify. It's pretty simple. Just got to know where to put the parentheses on your calculator. Okay, so now this is where the critical value method and the p-value method diverge. So those two methods are starting in exactly the same way. Then the p-value method picks up here. This is where you'll make a decision about the null hypothesis relative to our desired significance level. In order to do that, you'll classify the test as two-tailed, left-tailed, or right-tailed. You'll find the p-value using the area associated with the test statistic. If it's two-tailed, p-value is double the area in the nearest tail. If the test is left-tailed, p is the area in the left tail beyond the test statistic. And if the test is right-tailed, the p-value is the area in the right tail beyond the test statistic. And then we'll make a decision about the null hypothesis. We're going to compare p to our significance level alpha. If p is less than or equal to alpha, then we're saying that something that was supposed to be highly improbable is actually happening. So in that case, we're going to reject the assumption that led us to believe that this event would be improbable. So that means we're going to reject the null hypothesis. In that case, our test statistic is significantly high or significantly low, which means that x sub 1 bar minus x sub 2 bar is significantly high or significantly low. Now, if p is greater than alpha, that's saying that this event is likely to occur or may easily occur due to chance, given that the null hypothesis is true. So we're not going to accept the null hypothesis, but we'll fail to reject it. What we're saying is that the null hypothesis might be true. We can't prove that it's true, but we can say that there's not enough evidence to suggest that it's not true, so we'll fail to reject the null hypothesis. And then lastly, we want to state our conclusion about the original claim in non-technical terms, because no one should have to take a statistics class to understand where we're coming from. Now, before we get into our first example, I just wanted to recap some of the characteristics of the student t distribution. We've seen this before. They have slightly different shapes for different sample sizes. So this green distribution is the standard normal distribution. This maroon one is a student t distribution with a sample size of 12. And this blue one is a student t distribution with a sample size of 3. As n increases, the student t distribution gets closer to that standard normal distribution. And it has the same mean as a standard normal distribution. The distribution has a mean of 0, but the variation is larger. It's more spread out. The standard deviation of a student t distribution is larger than 1. But notice that it still has that same symmetry and that same bell shape as the standard normal distribution. It just has greater variability, which is measured in terms of that standard deviation being greater than 1. And that would be expected whenever you have small sample sizes. If you're computing means of data sets with small samples, so you take 3 values and then you compute their mean, and then you choose 3 different values from your original population, and then you compute their mean, well, you would expect to have more variation there than if you picked 30 values or 50 values from that larger population. So I would expect variability to increase when I'm making small samples, because there's just more variation due to chance when you're only choosing a few values, as opposed to when you're choosing more and then computing means. And I just mentioned that the mean is 0 and the standard deviation is greater than 1. And that standard deviation depends on the number of degrees of freedom of that test statistic. So this slide is about the test statistic in degrees of freedom. Our test statistic is a t-score, and it's found using this formula as we discussed earlier. Now, the degrees of freedom is associated with a particular data set, and it's associated with a sample size. So the degrees of freedom are going to help you distinguish between student t-distributions. You've got lots of them. You've got one for every sample size. The question is, which one are you talking about? Well, we could specify which student t-distribution we want based on sample size, but typically we don't do that. We associate it with a particular number of degrees of freedom. Now, we can use a conservative estimate of the number of degrees of freedom, which is the minimum of one less than the sample size for each of those 2 samples. So you take each sample size, you subtract 1, you look at the 2 numbers, and you say which one's smaller. That's the number of degrees of freedom. Now, we say that this is a conservative estimate because what we mean by that is that when we do a hypothesis test using this conservative estimate of the number of degrees of freedom, the hypothesis test will be less likely to lead to a rejection of the null hypothesis than a test using the exact number of degrees of freedom. Or in other words, that range of values of the test statistic or the corresponding sample statistic, x sub 1 bar minus x sub 2 bar, for which we choose not to reject the null hypothesis, that range of values in the middle is going to be larger with this conservative estimate of the degrees of freedom. So we're erring on the side of not rejecting the null hypothesis, and this conservative estimate will lead us to be less likely to reject that null hypothesis. Now, if we want the exact value of degrees of freedom, we can use this formula here, where a and b are s sub 1 squared over n sub 1 and s sub 2 squared over n sub 2. Notice that that is what you have here in your formula for that standard deviation in the denominator for our test statistic t. A is the approximate standard deviation squared, or approximate variance of the distribution of x sub 1 bar. And b is the approximation of the variance of the distribution of x sub 2 bar. If you compute a and b using those formulas, sorry, I'm trying to get my mouse back. There we go. You compute a and b using those formulas, and you use this formula, you can get the exact number of degrees of freedom, which is generally higher than the number of degrees of freedom over here. But that's going to be more precise and more likely to correctly reject the null hypothesis or fail to reject the null hypothesis than it would with this conservative estimate over here. Now, when we're computing p-values and critical values, it's just like we talked about before. We're going to use technology for p-values, and the critical values can be found using table A3 in the Triola formulas and tables. And that table lists critical values of t for different numbers of degrees of freedom, and also for area in one tail or area in two tails for commonly used areas, like an area of 0.01 in one tail or two tails, or 0.5 or 0.05 or 0.10 or something like that. So you're going to know what the area in one or two tails is. And then in the right-hand column, you'll look for the right number of degrees of freedom, and you'll just see where the columns and the rows overlap in order to find the appropriate critical value or values of T for your hypothesis test. Okay, so that is the background. That is the rationale behind the p-value method, the critical value method, and the confidence interval method. It's all based on that sampling distribution of a sample mean, and then taking that sampling distribution of a sample mean and turning it into a distribution of a difference between two sample means. And then using the student T distribution because we don't actually know the population standard deviation of either population. Okay, now let's apply these ideas, and specifically, let's focus on the p-value method for a difference between two means in this example. So here's the problem statement. It says, researchers from the University of British Columbia conducted trials to investigate the effects of color on creativity. Subjects with a red background were asked to think of creative uses for brick. Other subjects with a blue background were given the same task. Results were scored by a panel of judges, and results from scores of creativity are given below, or actually to the right in this case. Higher scores correspond to more creativity. The researchers make the claim that blue enhances performance on a creative task. We're asked to use a 0.01 significance level to test the claim. Now, if I was giving you an exam, I might just give you this problem statement and a piece of paper and ask you to do this. But if we're doing exams or quizzes or homework on MyLab statistics, they're probably going to break this down into a number of steps. When they do, this is what they typically ask you for. They ask you to identify the null and alternative hypotheses. They ask you for the test statistic, and then they ask you for the p-value. Then they ask you to state a conclusion about the null hypothesis. So that's whether you fail to reject the null or you reject the null. And then they want a final conclusion that addresses the original claim. So that's the plan. And we've got this data over here on our right. Okay, so the first thing we need to do is check the requirements. Well, we're not told the population standard deviations, and we have no reason to assume that they're equal to each other. So that's satisfied. We can assume that these samples are independent samples, and they are simple random samples. And we did see, if we look on that last slide, oops, sorry, there it is. The sample sizes were 35 and 36. So both sample sizes are larger than 30. And that is enough for us to assume that the sampling distribution of the sample means, or the difference between the sample means, is approximately normal. Okay. So our requirements are met. Now we just want to identify the null and alternative hypotheses. Now the claim was that blue enhances performance on a creative task, and they said that the values or higher values were associated with higher ratings of creativity. So what they're saying is that the mean score for creativity, when they had a blue background or they were in the presence of this blue color, must be greater than the mean creativity score for people with a red background. Now, it's maybe hard to remember. Oops. But our first group, our first population was the red group, and our second population was the blue group. So when they say that blue enhances performance on a creative task, what they're saying is that the mean for the blue group is greater than the mean for the red group, which means that the population mean for the second group is greater than the population mean for the first group. Now, if that's not true, the population mean for the second group would have to be less than or equal to the population mean for the first group. Now, if you're looking on MyLab statistics, they're never going to put mu sub 2 first. They're always going to put mu sub 1 first. So we would look at these two inequalities. We would say which one does not contain the condition of equality. That's the first one. and that would be the alternative hypothesis. But we want to write it the opposite way so that mu sub 1 is first. If mu sub 2 is greater than mu sub 1, then mu sub 1 is less than mu sub 2. You just flip it and write it the other way. That's the claim, and that happens to be the alternative hypothesis in this case. And then if I want the null hypothesis, I just take the claim and I take that less than sign and I replace it with an equals sign. Okay, so now I know what my null hypothesis is, and then we want to either identify or compute the sample sizes, sample means, and sample standard deviations, and those are given to us right here. The sample sizes are 35 and 36. The sample means are 3.39 and 3.97, and the sample standard deviations are 0.97 and 0.63. And then just to make sure we actually understand what it is we're doing and why, I'd like to graph the sampling distribution of x sub 1 bar minus x sub 2 bar, assuming that the null hypothesis is true, which is the same as assuming that the mean is 0 of the distribution of x sub 1 bar minus x sub 2 bar, and then label the sample statistic that we have on our graph. So x sub 1 bar minus x sub 2 bar turns out to be 3.39 minus 3.97, and we get about exactly negative 0.58. So my mean is 0, negative 0.58 is going to be to the left of that. And we're asking ourselves, is that significantly high or significantly low, given that the mean of the distribution of x sub 1 bar minus x sub 2 bar is 0? Or in other words, given that the two population means are equal to each other. So mu sub 1 is equal to mu sub 2. Saying, if that's true, is it significant that we have a difference between sample means of negative 0.58? In order to figure that out, we are going to compute the test statistic t corresponding to that difference. The test statistic t comes from just using this formula. In the numerator, we substitute in our x sub 1 bar and x sub 2 bar. And then mu sub 1 minus mu sub 2 is the assumed value in our null hypothesis. Well, that is assumed to be 0 in our null hypothesis. So we're not subtracting anything from this difference. And then we just substitute in the two sample standard deviations, 0.97 and 0.63, and we substitute in the two sample sizes, 35 and 36. If we use Excel to do arithmetic or we use a calculator to do arithmetic, we get negative 2.98 as our test statistic t. So this is not to scale, but we're taking this distribution of x sub 1 bar minus x sub 2 bar and we're converting it to the student t distribution like this. And then we say to ourselves, okay, is that test statistic? T sub test equals negative 2.98, significantly high or significantly low. In order to answer that question, we want to find the p-value that is associated with that test statistic. And finding the p-value requires us to think about whether the test is two-tailed or left-tailed or right-tailed. So in order to do that, we have to look at the alternative hypothesis. Since mu sub 1 is less than mu sub 2, we can think of that as an arrow pointing to the left. What we have here is a left-tailed test. Then we want to compute the number of degrees of freedom for our data. That's important because you need the number of degrees of freedom in order to choose the correct student t distribution in order to get the area in that left tail that we'll need for the p-value method. Now you've got two possible degrees of freedom. You can use the conservative estimate. The degrees of freedom could be, we could use the degrees of freedom are equal to the minimum of the first sample size minus 1 and the second sample size minus 1. So the minimum of 34 and 35, which is 34. Or we could use this formula for the exact number of degrees of freedom. If A and B are given by these estimates of the variance, excuse me, of x sub 1 bar and x sub 2 bar, then if A and B are those values, df is actually equal to that expression in the denominator. If I use Excel to find that value, I get 58.11. Now, I'm not doing any of this computation here in this video, but I do a lot of this computation for the p-value method with the conservative estimate of the degrees of freedom and the exact value of the degrees of freedom in the homework help videos. So you might want to check out the statistics homework help videos if you want to see exactly how this is entered into Excel and how I am getting Excel to do all these calculations for me. Okay, so now I have, I know I'm doing a left-tailed test and I have the number of degrees of freedom. So now I want to find the area to the left of my test statistic, because it's a left-tailed test, using either Excel or table A3, not A2. So remember, our p-value with the left-tailed test is just the area to the left of the test statistic. So it's the probability that our test statistic is less than or equal to -2.98. Using Excel, we get this as our p-value when we use the exact number of degrees of freedom. And using the conservative estimate of the number of degrees of freedom, using this function, I get this. Actually, I think I need to use Excel for this. I just told you that I wasn't going to use Excel, but I want to show you how to do this computation. So I'm going to pause here and then I'll start recording again once I've got Excel open, and we'll do some of these calculations together. Okay, so I'm in Excel and I've created a spreadsheet and I've included the summary statistics that I was given. I have the sample size, X sub 1 bar and S sub 1. I've got the sample size, X sub 2 bar and S sub 2. Now, if I want to compute A and B, which are a good idea, that is a good idea to compute those because I need them for the estimated standard deviation formula as well as for the exact value of the number of degrees of freedom. I'll calculate those here. So A is an estimate of the variance for that first sample, and that comes from taking the sample standard deviation and then squaring it, and then taking that value, there we go, taking that value and then dividing by the sample size. And then B is the same thing. Over here, you just use the sample standard deviation for the second sample, and then you divide by that sample size. In order to compute our test statistic, we need X sub 1 bar minus X sub 2 bar. So I'll take that here. For the estimate of the standard deviation, that's in the denominator. You're going to take the square root of A plus B. And then our test statistic T is given by X sub 1 bar minus X sub 2 bar minus 0. That is the assumed value of mu sub 1 minus mu sub 2 in the null hypothesis. And we divide by the estimated standard deviation. So that's the same test statistic T that I got on my slides. Now, if I want the exact number of degrees of freedom, the numerator was A plus B quantity squared. So I'm just going to type open parentheses or equals open parentheses A plus B close parentheses quantity squared. And then the denominator has A squared in it. And then you divide by the sample size minus 1. And then you add B squared, oops, it's open parentheses there, B squared, and then you divide by sample size minus 1. And we get that 2.47 times 10 to the negative 5. That's tiny. So then the exact number of degrees of freedom is given by this numerator divided by the denominator. And we get about 58.11, which is exactly what I had on the slide. Okay, so now if I want the p-value, there are two ways I can do that. I can do that with the exact number of degrees of freedom, and I can do that with the conservative estimate of the number of degrees of freedom, which is going to make it less likely that we'll reject the null hypothesis. I need the area to the left of the test statistic. So I'll type equals t.dist, open parentheses, and Excel will remind you what you're supposed to type in here. So we'll select the test statistic, the number of degrees of freedom for the exact number of degrees of freedom, those are right there. And when it asks for cumulative, that's just saying, do you want the area to the left or not? And I want to say yes. So we type true. And then for the conservative estimate of the number of degrees of freedom, the p-value is still given by the same formula, t.dist in Excel, and you enter the test statistic. But this time for the number of degrees of freedom, rather than using this 58 degrees of freedom approximately, you're looking at the two sample sizes, which were up here. You've got 35 and 36. You subtract 1 from each of those, so you get 34 and 35, and you take the smaller of those two. So we have 34 degrees of freedom. We still want to say, yes, we want the area to the left. Look at the difference in the p-values. It's very small. One is 0.00210. This one is 0.00265. So the difference between this one and this one is 0.00055 approximately. That's a very small difference. And it's not a difference that actually makes a difference when it comes to rejecting or failing to reject the null hypothesis. So you see, even though the number of degrees of freedom are very different, one was 34 degrees of freedom and then one was more than 58 degrees of freedom, the p-values were very close. They weren't exactly the same, but they were very close, and they are both going to lead to the same result as far as our null hypothesis is concerned. So if you are one of those people who says, I don't want to use the conservative estimate, I want to make sure I use the exact DF every time, I would say it's okay to use that conservative estimate, the minimum of those two numbers. It's really easy to compute, and the difference in the p-values tends to be so small that using the conservative estimate does not change the result of the hypothesis test. Okay, let's go back to our slides. So we said we have this conservative estimate for the degrees of freedom. We have this exact value of the degrees of freedom. And we want area to the left because it's a left-tailed test. And we can use either of these functions in Excel. And we get the same values that I just showed you in Excel. That's how I got these values when I made the slides to begin with. And then you take the p-value, either one would be fine, and you compare it to alpha. Now, our significance level alpha in this case is 0.01. Obviously, both of those p-values are less than 0.01. So what that's telling us is that the chance of getting a test statistic as extreme as ours or more extreme is very low. And that's the same chance as getting an x bar minus x, or x sub 1 bar minus x sub 2 bar as extreme as ours or more extreme than ours. So the chances of getting an x sub 1 bar minus x sub 2 bar like that are significantly low. They're very low, given that the null hypothesis is true. So if something that's highly improbable is happening, and we say that it's highly improbable because we're assuming that the null hypothesis is true, maybe the null hypothesis isn't true. So we're going to reject the null hypothesis. Remember, you have that mnemonic as well. If you want, you can remember, if P is low, the null must go. If P is high relative to alpha, the null can fly. So we see that we're rejecting the null hypothesis. Now we want to state the conclusion in terms of the original claim. So our claim was that mu sub 1 was less than mu sub 2. So the claim does not contain the condition of equality. The claim is the alternative hypothesis. So if we're rejecting the null hypothesis, we're actually supporting the original claim. So that means we will say that there is sufficient evidence to support the claim that blue enhances performance on a creative task. That's using the p-value method. In the next video, we're going to work the same example all over again, this time using the critical value method. We're going to see that we get exactly the same results. The critical value method starts in very much the same way as the p-value method. We just compare critical values to the test statistic, or look at whether that test statistic is in the critical region, rather than comparing areas and probabilities as we did in this video. So I'll see you in the next one to discuss the critical value method.